Have you ever looked up at the sky and marveled at the power of a jet airplane soaring through the air? The sight of these magnificent machines cutting through the clouds is nothing short of awe-inspiring. That incredible force propelling the aircraft is generated by a marvel of engineering, the jet engine. It's a testament to human ingenuity and our relentless pursuit of progress. These powerful machines have revolutionized air travel, making it possible to traverse vast distances at incredible speeds. Imagine crossing continents in mere hours, a feat that was once the stuff of dreams. The basic principle behind jet engines is remarkably simple, yet the technology itself is incredibly sophisticated. It's a blend of physics, engineering, and sheer innovation. In essence, jet engines generate thrust, the force that propels an aircraft forward, by harnessing the power of burning fuel to create a continuous high-velocity jet of exhaust gas. This thrust is what allows airplanes to take off, climb, and cruise at high altitudes. This process, based on Newton's third law of motion, for every action there is an equal and opposite reaction, is the fundamental principle behind jet propulsion. It's a principle that has been harnessed to achieve incredible feats of engineering. The development of the jet engine marked a turning point in aviation history, ushering in the jet age and transforming the way we travel the world. It opened up new possibilities and shrank the world, making distant places more accessible. From the earliest jet-powered aircraft to the sophisticated airliners of today, jet engines have continued to evolve, becoming more powerful, efficient, and reliable. Each generation of engines brings new advancements and improvements. In this exploration of jet engines, we will delve into the inner workings of these incredible machines, understanding the fundamental principles that govern their operation. We will uncover the secrets behind their power and efficiency. We will examine the key components of a jet engine, follow the journey of air as it is drawn in and expelled, and discuss the crucial role of fuel and combustion in generating thrust. Each part plays a vital role in the overall performance of the engine. Let's embark on a journey to unravel the mysteries behind the roar of innovation that propels us across the skies. Together, we will discover how these marvels of engineering continue to shape our world and our future. At the heart of every jet engine lies a symphony of meticulously engineered parts working in perfect harmony. Each component, no matter how small, plays a crucial role in the overall performance and efficiency of the engine. These components, each playing a vital role in the engine's operation, can be broadly categorized into a few key sections: the compressor, the combustion chamber, the turbine, and the nozzle. Each section is designed with precision to ensure optimal performance under extreme conditions. The compressor, situated at the front of the engine, is responsible for drawing in vast quantities of air and compressing it to extremely high pressures. This process is essential for the subsequent stages of the engine's operation. Think of it as a giant fan that sucks in air and squeezes it into a smaller space, increasing its density and potential energy. The compressed air is then directed towards the combustion chamber. The combustion chamber, located downstream of the compressor, is where the magic happens. It's here that the engine's power is generated. Here, the highly compressed air is mixed with fuel and ignited, creating a continuous, controlled explosion that releases a tremendous amount of energy. This energy is what propels the aircraft forward. This intense heat causes the air and combustion gases to expand rapidly. The expanding gases are then channeled towards the turbine. Next comes the turbine, a set of rotating blades positioned in the path of the expanding hot gases. The turbine is a critical component that converts thermal energy into mechanical energy. As these gases rush past the turbine blades, they impart their energy, causing the turbine to spin rapidly. This spinning motion is essential for the engine's continuous operation. This rotational energy is then used to power the compressor at the front of the engine, ensuring a continuous flow of air. This interdependence of components is what makes the jet engine so efficient. Finally, the exhaust gases, still carrying significant energy, exit the engine through the nozzle. The nozzle's design is crucial for maximizing the engine's thrust. The nozzle is a carefully shaped duct that accelerates the exhaust gases to extremely high velocities, creating a powerful jet of hot gas that propels the aircraft forward. This final stage is what gives the jet engine its incredible power and efficiency. The journey of air through a jet engine begins with the compressor, a marvel of aerodynamic design that plays a pivotal role in the engine's operation. Imagine a giant fan, its blades meticulously shaped to efficiently draw in vast quantities of air and compress it to extraordinary pressures. As the aircraft moves forward, air is forced into the engine's intake, where it encounters the first stage of the compressor. The compressor consists of a series of rotating blades known as rotor blades and stationary blades called stator blades. The rotor blades, attached to a rotating shaft, accelerate the air as it passes through them, increasing its velocity and kinetic energy. The stator blades, fixed to the engine casing, then direct the fast-moving air into the next stage of the compressor, where the process of compression continues. Stage by stage, the air is compressed to higher and higher pressures, its density increasing with each successive stage. This compression is crucial because it allows a greater mass of air to be squeezed into the combustion chamber, ultimately leading to more powerful combustion and thrust generation. The compressor's ability to efficiently compress large volumes of air is paramount to the performance of a jet engine. The higher the compression ratio, the more thrust the engine can produce, enabling greater aircraft speeds and payloads. Section 4. Igniting the power, fuel and combustion. With the air compressed to immense pressures, the stage is set for the heart of the jet engine's power generation, combustion. Within the combustion chamber, a continuous, controlled explosion unleashes the energy stored within the fuel, transforming it into heat and expanding gases that drive the engine's operation. As the highly compressed air enters the combustion chamber, it is mixed with atomized fuel, typically kerosene-based jet fuel. This fuel-air mixture is then ignited by a continuous spark or flame, creating a sustained combustion process. The combustion chamber is designed to withstand the intense heat and pressures generated during this process. Its walls are lined with heat-resistant materials that can endure temperatures exceeding 2000 degrees Celsius. The combustion process is not a single explosive event, but rather a continuous, controlled burn. Fuel is continuously injected and ignited, ensuring a steady stream of hot, expanding gases that flow towards the turbine. The efficiency of the combustion process is critical to the overall performance of the jet engine. Ideally, all of the fuel should be burned completely, releasing its maximum energy. However, in reality, some unburned fuel and other emissions are produced, which have environmental implications. Section 5. Creating thrust newtons, third law in action. The heart of a jet engine's power lies in its ability to generate thrust, the force that propels an aircraft forward. This thrust is what allows massive airplanes to lift off the ground and soar through the skies, defying gravity and covering vast distances in relatively short periods of time. This thrust is a direct consequence of Newton's third law of motion. For every action, there is an equal and opposite reaction. In the context of a jet engine, the action is the expulsion of exhaust gases out of the engine, and the reaction is the forward thrust that propels the aircraft. As the hot expanding gases generated in the combustion chamber rush towards the rear of the engine, they encounter the turbine, a series of rotating blades connected to a shaft. This process is crucial for converting the energy from the combustion into mechanical energy. The force of these gases pushing against the turbine blades causes the turbine to spin rapidly, much like a windmill harnessing the power of the wind. This spinning motion is essential for the next stages of the engine's operation. This rotational energy, extracted by the turbine, is then transmitted back to the front of the engine via the shaft, where it powers the compressor, ensuring a continuous flow of air through the engine. The compressor's role is to increase the pressure of the incoming air before it enters the combustion chamber. The exhaust gases, still carrying significant energy after passing through the turbine, are then channeled through the nozzle, a carefully shaped duct at the rear of the engine. The design of the nozzle is critical for maximizing the efficiency of the thrust generation process. The nozzle acts as a converging-diverging passage designed to accelerate the exhaust gases to extremely high velocities. This acceleration is key to producing the powerful thrust needed for flight. As the exhaust gases are squeezed through the nozzle's converging section, their velocity increases. This increase in velocity is a direct application of fluid dynamics principles. Then, as they pass through the diverging section, their pressure decreases while their velocity increases even further. This process ensures that the exhaust gases exit the nozzle at maximum speed. This high-velocity jet of exhaust gas exiting the nozzle creates the thrust that propels the aircraft forward. The efficiency of this process is what allows modern jet engines to achieve such remarkable performance. The greater the mass flow rate of exhaust gases and the higher their exit velocity, the greater the thrust produced by the engine. Engineers continuously work on improving these parameters to enhance the performance and efficiency of jet engines. This thrust force overcomes the drag acting on the aircraft, allowing it to achieve and maintain flight. By understanding and applying Newton's third law, engineers have been able to design engines that make air travel faster, safer, and more efficient.